So, Ravi, go ahead and take it away.
Yeah, thanks, Trio. Hello, everyone. So today we'll be talking about Tesseract, a project that we used at Gojek for terraforming scalable and reproducible infrastructure. So a little bit about me. My name is Ravi Suhag, and I'm VP of Engineering for the data platform here at Gojek. So today's agenda is going to be, we're going to talk about some of the challenges we face for creating and provisioning infrastructure, and what are the certain objectives that we wanted to achieve with this entire exercise, how the architecture looked like, what was the impact of it, and what are the some very short and concise lessons that we learned through this whole exercise. So let's talk about challenges first. So if you look at the Gojek infrastructure, we have more than 500 services which are spread across multiple data centers to serve the best need of our customers, right? And to support these services are spun across 50 plus GCP as well as AWS projects, more than 200 networks. And we have a lot of clusters running, clusters like Kubernetes, Kafka clusters, Spring clusters running across all these projects. And all of this is then backed by compute machines across AWS and GCP cloud providers. We have more than 3,000 plus these machines running, which kind of take care of the microservices as well as the databases. So first challenge that comes is the expansion of the infrastructure. So whenever there is a new launch of the country, right, or there is a new launch of the product. So now we introduce, let's say, a new product, or we are expanding to a new country. And then there is a clear need of that, hey, now we have to spin up the whole data infrastructure from ground up for that particular product. And then there is a need to basically making sure that all of this infrastructure for all running the data pipelines as well as the microservices is available for those teams and the products. On top of that, all the teams are distributed across different locations. So we have teams in Bangalore, Singapore, as well as in Jakarta. And all of these teams require different needs, and then teams are very distributed. So it becomes very challenging in terms of coordinate, hey, how much infrastructure that is team going to need. And each team has different needs in terms of how much infrastructure and what type of infrastructure they need. So this distributed teams and the infrastructures make it also a bit tricky in terms of how do you provide consistent infrastructure tooling and then scaling for all of these distributed teams. Another need is that, okay, now if some product is ramping up or some product is kind of slowing down, then you need to auto scale your infrastructure as per the needs. And you don't want to end up into spending a lot of hours of your team to scale up the infrastructure when it's growing, or just downscaling it when it's there. You kind of bit of need want the auto scaling on that entire infrastructure. So certain objectives we wanted to achieve with this exercise, and what we thought moving into that direction will help us. One is that we wanted to make sure that entire infrastructure is declarative. So engineers can basically look at the infrastructure and then very clearly tell what is deployed, what is configured, without worrying about the past state of the infrastructure or how it has evolved in the past. How many engineers have made changes to that infrastructure? No one should be worrying about that particular case. In case they want to look in the history, they should be able to look at it, right? But they should care about what is the current state of the infrastructure and how does it look like and how does the networking look like. Structure and consistency is what also we wanted to achieve in terms of there should be a consistent workflow in the code structure, and everyone should follow the same. Does not matter which team is asking for this infrastructure and which team is creating this infrastructure. Irrespective of that, they should follow a clear, consistent structure, that there is a single module to spin up Kafka cluster, and that the same module should be followed by everyone else. It should not be like someone is writing, let's say, Terraform code for this team separately, but team B is writing it in a very different fashion. Another thing is that we do not want the core infrastructure team to be blocked, other teams to be blocked by that core team. We wanted a very self-service model where engineers can decide and then pick, and then they can on their own provision this infrastructure on demand. And again, same in the consistent fashion. Operations should be there, right? It should not be the case that anyone should be able to run these pipelines or these CI/CD pipelines to run the infrastructure or to deploy it. The user should be authorized that, hey, who is able to basically deploy these infrastructure and deploy these pipelines, and then there should be a whole governance around it. Accountability is another piece where in terms of we need to very clearly know who owns this infrastructure, who is the right team for it. If something wrong happens, who should be the first L1, L2 support. So there should be a complete accountability around that entire infrastructure. So now to achieve all of that, I'll present how the architecture look like. And this is just a very simplified high-level architecture of this, where we have this entire place where user starts from, and then they write the infrastructure as code, and which is mostly come into HCL language, HashiCorp language, which is also used in the Terraform. And then we have a in-house built registry, which has a lot of things. One, it has a lot of Terraform modules. Even the Helm charts, for example, they are also stored into that registry. Or even we use Chef for cookbook and compute configuration. So even your cookbook should be basically part of the same registry. So this registry contains all these reusable modules. And then users use this registry. And then we have a system called Tesseract, which is a combination of CLI tool plus infrastructure as code. And then they basically use those registry, apply their whatever they want to create. And then that goes through the CI pipeline where the entire Terraform plan and apply happens. And then cloud infrastructure get deployed. But apart from that, when this Terraform apply is happening, we have a lot of custom Terraform providers written in-house. And those Terraform providers, they collect all the metadata from this infrastructure, all the secrets. Even when you create a resource, for example, if you create a Flink cluster, what is the URL domain, URL for that particular Flink cluster, how many task slot it has. If it is Kafka, then how many brokers it has. All of these details, they flow through these Terraform providers, custom written Terraform providers, and that goes into the metadata. It goes into the TF state, and we have an in-house service called Apollo, which is the metadata service. And all of that service basically captures this. And then on top of that metadata, then we have auditing in terms of, hey, this user should be given access to this infrastructure, but from the cloud infrastructure, this is the user which has it. So the whole auditing and then analysis of that metadata also happens into the last auditing piece. So first piece of this entire thing is module registry. So we have a self-hosted GitLab registry. We host it on the GitLab of a lot of Terraform modules and providers. And then they span across, there is a Kafka provider. There is a module for the Flink, there is a module for the Airflow, and so on and so on. So how does the modules look like? So all these modules are self-hosted on GitLab. So each module is basically formed as a one repository into our source control. And we have 100+ modules in the entire registry, which are meant for different things. One is for Kafka, Flink, Kubernetes, and like that. And this is just a sample of how they look like. This sample does not have all the configurations that you could provide, but this is how it looks like. And then we basically provide the Git URL path, and then the whole URL of the registry. And the entire version controlling also happens through the ref tag of the Git tag. So basically, just with the simple GitLab repository, we are able to very effectively host the entire module registry. Now, once the module registry in place, and anyone wants to come and then create a cluster, and that could be anything for example, even if they want to just create a tunnel between two GCP projects, or they want to create a Kafka cluster or a mirror maker for that example. So we have written a custom tool on top of it, which basically takes the input and output of this registry. Hey, what should be the input for this module and that module, and wraps it up into an interactive CLI tool, where you can just simply go say entropy provision, and then it shows you what all kind of tools modules that you can use for registration. And once you say entropy provision, let's say Kubernetes, it asks you for the right parameters that you can just simply submit, and it auto generates the entire Terraform code that you need to generate, you need to use for applying it, and it puts it into the right place and right directory. And after that, it's simply that you can just go and do the Terraform apply. So the this generation of the code for writing anyone like the Terraform code, that is something that we have completely abstracted out. These modules, as long as they exist, people should be able to provide simple configuration and parameters, and able to basically generate this code and apply it right away. This helps them in terms of reducing the overall time that people need to basically write the Terraform tooling and code. Second thing is that now a lot of teams are spinning up these networks and the projects. We used to face a challenge where how do you allocate the subnet and then IP addresses to each of these clusters and networks and then VPCs. So what we have done is we've written an internal service that we call Ghana, which is like assigned number authority. And then we wrote a custom provider on top of that, which basically can say that if I'm creating like a Kubernetes cluster and then to provide a network range for it, I can just simply tell it, oh, this is my project, my category is, let's say, VPC, my network name is this, and then just allocate me a subnet. And then you can use that subnet to basically provide it into it. We also have a data resource for the same Terraform provider, where you can fetch the detail of a certain subnet. If you have to, let's say, if you're creating tunnel between two VPCs, and I want to fetch the detail of a subnet from the other one, I can simply provide the project name and category, and then I can fetch the detail of that subnet also. So this way we are able to basically completely have a central repository and then prevent all IP ranges from clashing also. So anyone can go and simply and safely create any cluster without worrying about if the IP range or the configuration of this might overlap with something else. So this is the custom metadata provider that I talked about. What this metadata provider does is that it stores all the metadata of the infrastructure that we have provisioned into a central repository. So as soon as I create a cluster or any other resource through that, it can send, for example, for Kafka, what we collect is that, hey, what is the name of the cluster? What is the bootstrap server URL? How many brokers it has? What are the IP addresses of the brokers? So instead of, if someone wants to just basically utilize this metadata or even use this metadata into spinning up a new Kafka consumer, they should not be going in manually or checking it out from Git repository or from the Terraform code and then doing it. They can simply access it through the API. So all of this data is pushed through this metadata Terraform provider to this central repository of the metadata, and then everyone can just basically access that entire metadata from the APIs. So what was basically the impact of it? The major one is that we were able to reduce the time to provision by huge margin. Like, it used to take weeks to spin up the infrastructure of a Kafka cluster. You have to spin up the machines. You have to reach out you have to do the planning, how many brokers they want, how many in those brokers, what should be the disk size, what should be the other parameters, then configuring that entire cluster, then basically spinning up the monitoring of this, and then spinning up a Grafana dashboard on top of it, right? So there used to be a week time, a turnaround time for spinning up the Kafka cluster earlier. And now with the entire module registry and the Tesseract ecosystem, now it takes us 4 minutes to provision that entire cluster. And it takes from end to end, spinning up your machine to setting up your monitoring and creating a Grafana dashboard. End to end, everything happens through the same workflow. Operations became easy. So now we have this Git workflow and then this CLI tool. So people don't even have to ask us which module to use and how to use that Terraform module. They can just simply use the interactive CLI tool to provision it on their own. And we have a complete wiki of what tools, what modules are available into that registry. And then we have a discovery of that. So they don't even have to file a support ticket to the infrastructure team and asking that, hey, can you spin up this infrastructure for us? They can just simply use the CLI tool. So the entire operations kind of went away for us, and it became very, very simple to provision this infrastructure. Some very quick lessons on using Terraform and the whole infrastructure as code. Make sure your blast radius is limited. You don't want one module or one piece of the code to impact the other part of it. If someone make a mistake by chance, then it should not be impacting the rest of the infrastructure. So we maintain it at the very minimum level. So our blast radius goes up to a single cluster instead of we dumping entire code into a single folder and then Terraform applying happening there. We have a very structured where the top level entity is there, then VPCs below that clusters, and we go up to clusters. We don't go blast radius reducing it up to a machine, but up to a cluster. So a single Kafka cluster, for example, will have its own state maintained separately, and the Terraform apply will happen within that only. This does create a lot of hierarchy of multiple folders within your infrastructure as code. But with the CLI tool that we have built on top of it, it allows us to basically put it into the right place and then structure it well. So that solves the problem of people figuring out where exactly should be the location of this infrastructure and where should I put my code. But yeah, this practices allow us from making sure that people do not affect the other part of the infrastructure when they're making a change. Another thing we learned is, and which is very easy to actually miss out on, is the naming. Whenever you create your infrastructure, it is very easy to basically just call it whatever we want to. But what we do is, and that basically comes back and bite you back. in terms of, hey, you're not able to figure out what exactly that machine was for. Like you don't want to call your microservice some XYZ characters. You want it to be name it what it should be. It should tell you very clearly what infrastructure, which environment it is hosted on. So we follow very consistent naming. So for example, one of the sample machine or cluster name could look like for us is that let's say Gojek or food, and then mainstream Kafka, like that, right? So it follows a clear, consistent naming convention, and then there are clear rules defined that, hey, this is how the name should be prepared. So people will say, what is my team name, which environment I'm deploying it on, and behind the scene, the module